this. Whenever you encounter a scenario where you're driving, okay, and the other person's navigating, and you have a good idea of what's going on, but the person who's navigating doesn't seem to, it's perfectly fine to say, hey, you know, since you're kind of struggling with this and I know what's going on, why don't we flip? I'll start navigating and you start driving, okay? So I know that's not super practical right now just because of the whole screen share thing, but I mean, it's pretty straightforward to just copy your code, throw it in Slack, other person copy it out really quick. So really that's the point at which you should switch, okay? If you're grinding, and that's the rule. I think I told you guys this at the beginning, no grinding, right? If you're sitting there and you don't have an idea of what to do, try at that point to switch. And if you still have no idea what to do, message me, throw something in the chat, you know, and I'll try to get you help as soon as possible. Okay? Does that answer your question? Sweet. All right, cool guys. All right, really quick. Can I see a B in the chat if you were able to complete the warm-up completely? Complete it completely. All right. Okay, guys. So, like I mentioned, I shouldn't mention this, but that warm up was really mostly a refresher from last class. Okay. So if you were experiencing trouble with that, I mean, that's the kind of thing we ideally want to shoot for warm ups being like, you know, 15 to 20, maybe like a half hour tops. That was about a little over a half hour. So if you're experiencing trouble like finishing that in the time period, definitely like try to schedule office hours so that you can really grind those concepts. You know, if you're having trouble with conditionals, if you're having trouble with, you know, fixing syntax errors, just like get some office hours. Say, hey, Tyrus, can we go over this a little bit just so I can really lock it down? Especially with this beginning stuff, you know, it's the kind of stuff that you don't want to have to think about, you know, how to do it when you're trying to do more complicated topics, because you want it to just be muscle memory of if conditional, boom, done thinking about it, right? So I see, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. See 11, so that's the majority of the class. If you were in the minority there, guys, like I said, please schedule office hours so we can get that worked out as quickly as possible. Let me check something really quick. Okay, cool. All right, we're good. All right, so with that, we can start with the lecture. So let me get on it really quick. Give me 1 second. I don't have it open. I got a note there. Oh, and in line with that really quick, that's something that Eric sort of touched on a little bit, but I just want to throw out there, there's a term called drive navigating. Okay, at no point ever in doing this should you be, you know, sitting there doing all the typing, doing all the talking, explaining what's going on, and the other person sitting there doing nothing. That's terrible. Never do that. Okay, if you're hitting a point where you really just, you know, don't get what's going on, maybe say, hey, either hit up me or do some Googling to try to figure it out. But one person, I guarantee you're not learning as much if you're not giving any input. It's just, that's how it works. That's at any subject, not just programming. So just wanted to throw that out there. You guys seem to be doing universally pretty good across the board, so I'm not too worried about it. I just wanted to, like, you know, say that right off the bat so you're used to doing it. Okay, cool. So we can, let's see, change this to... All right, so this is a decently long slide lecture. I think it's 35 slides, so we'll go through this, and then we will, you know, break off into the same pairs as before and start working through everything. All right, so sounds like someone might be unmuted. If you're unmuted, please try to mute yourself. All right, excellent. Repetition with functions. Okay, cool. All right, guys, so we've got 3 functions, right? And each one is raising a number to a certain power. We've written 2 of these before, and we call them square and cube, right? So square is pretty straightforward. It takes a number, and it returns that number times itself, okay? And that's the square of a number, okay? And then we have cube, which is it takes a number and, you know, multiplies it by itself 3 times to give you the cube of the number, okay? And then same thing with just power of 1, it just returns the number itself because anything to the 1 power is the number itself. So can I see some quick B's or P's in the chat? Does this make sense? Does anything here, is any part of this confusing or look unfamiliar? If so, I can go over it again. Cool. All right, B's across the board. Excellent. So if we wanted to add another function to this chain, because these are all doing very similar things, right? They're raising to different powers. we could do this, right? We could say power of 4 means take that same number and multiply it by itself 4 times so that it's doing the same thing, okay? And using this pattern, we can imagine that each one would look very similar, right? It just adds one more times base every time we went up. So if we did power 5, it would be 5 times. We'd have base 5 times with multiplication signs. 6, we'd have 6 times, and so on and so forth. But as you can imagine, that gets incredibly impractical, right? What if you wanted to do to the 50th power? You know, although that's an astronomically large number, it would also, you know, be a ridiculous function. You would never want to have to actually write that. Okay, so here's a question. How can we rewrite power of 4 to avoid having to type out base times base times base? So what else on this page could we use without introducing any new material? What could we do to simplify power of 4? Anybody have any ideas? Feel free to just throw them in the chat if you do. Anybody? It's okay if you don't, of course. No, because that is not a caret to the 4. Caret is not a operator in JavaScript to do powers. Caret is actually called a bitwise operator in case you want to deal in binary, but trust me, you don't right off the bat. Yeah, that's certainly a possibility, right? We could double up on power 2. We could say return power 2. That's actually not the answer that this slide deck was going for, but that's certainly a possibility, right? We could say that for power of 4, we could take power of 2 and just use it twice. We could say power of 2 times power of 2, and that would give you power of 4, right? Because it's really just a smaller part of a bigger problem, okay? But in the terms of this, right, we're just going to try to simplify it one step back at a time. So to raise the base to the power of 4, we can multiply the base by the results of the raising base to the power of 3, okay? So because this function returns base 3 times, we can just take out base 3 times here, okay, and put power of 3 in its place, okay? Because the result of base 3 times is going to be the exact same as base 3 times plus adding another base on, as I mentioned, every time you increase a power, okay? So this is kind of a crucial concept, okay? Does anyone not understand what we just did there? Okay, this is really important. So if you don't understand, please put a P so I can explain it again. Yeah, I mean B's and P's, but specifically P's is the important part here. Okay, and seriously, please, that's only like 8 people, guys. If you don't get what's going on, please tell me right now because you won't understand the rest of this lecture. Nobody? I'm seeing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Can we go for, how many people do we have in here? We've got 14 people. All right, I'm not seeing any B's, so I'm going to keep going, okay? All right, guys. So we're doing the exact same thing, right? Just repeating it. Okay, cool. So, and then we can reframe power of 3 in a very similar way, right? It's got the exact same thing in it as power of 2. It's got 2 base pairs, 2 base multiplied by themselves with an extra one added on. So we can instead replace that with power 2 of base, okay? Just B's or P's again. Is that a big leap and a bound to do that, or does that make sense? Okay. So this is kind of the concept of helper functions, right? If you have another function, keep in mind that when you're inside the curly braces, okay, you can write code as you normally would. So invoking another function just inside of a function is totally acceptable. You can just call it. That's fine. As long as it's, you know, if it's outside the function, you can call it just like this, okay? And that's what we would call a helper function in this case, okay? So it's using another function, but it's just calling it because they're in what's called, they're both in what's called the global scope. We'll talk about that a lot more later on. But for the time being, if you've got 2 functions in a file and they're outside of each other, excuse me, you can call one inside the other without any ramifications, okay? So in line with what we have here, you can kind of notice the trend, right? We can reframe power of 2 by calling power of 1 inside of it, okay? So as you'll see in a moment, rewriting power of 1 to look like our other power functions would be very helpful. Can you think of how we could do that? Anybody? Just throw in the chat. I don't want to put anybody on the spot for this, but if you have an idea of how we could possibly rewrite power of 1 in the same style as these other ones, please throw it in the chat. Think about what comes before raising something to the 1. Anybody? Don't be embarrassed. If you have an idea, just put it out there. Ideas are better than no ideas. Function of x. Well, so I mean, we already have a function that's only taking a number. It's only taking one number, just like all the other ones. So that doesn't say anything different. It's really like what the internal is, right? I mean, so look at our trend, right? 4, 3, 2, 1. What would we call the one before this? Yeah, power of 0, right? So we'd call it power of 0. It would take base, just like this. And then what would it do in that case? Yeah, Kai, perfect. It would return 1, right? Because any number raised to the 0th power is 1. Okay? So sure enough, if we had power of 0 in base, we could just return 1 by itself. And then we could then refactor power of 1 to use that helper function of power 0. Okay? So at the end of the day, right, we've got everything that's going on here is using the previous function before it, okay, to simply add on a new base call each time. So we're taking the previous result, and we're adding on times base, okay, and we're returning that. And the previous result, adding on times base and returning it, right? Same thing all the way up the tree. Okay, sorry, not tree, all the way up the list. Can I see B's or P's? Does everyone understand what's going on with this? How we're using the previous function and how they're all interconnected. Once again, excellent point at which to ask questions, otherwise the next part will be kind of a leap. Nobody? That's great. I mean, when I went through this slide deck, I was like, wow, whoever put this together is genius. Like, seriously, this is a great slideshow. I wish recursion had been taught to me like this. Like, seriously. All right, cool. So let's see. So as it says here, notice the symmetry except power of 0, right? We've got a previous call here, previous call, previous call, previous call, but nothing here because it's our, what we would call our base case, right? There's nothing else left to do. All right, so we'll stop here for now, okay, because we don't have to type out ever-lengthening series of times base with each new power n function, but we still have lots of repetition, right? At the end of the day, we could probably write a function, one function, that would do exactly all of this for us, but instead we have 5 functions, okay? Every time we want to calculate raising a number to a new power, we got to write another function. So what if we could create one function that will raise any number to any power? How might we write such a function? So let's put our functions aside and explore this possibility, right? We're going to call this function power since we want it to be able to calculate any exponent. Okay, and we know it's going to take 2 arguments because previously, right, we were taking just a base and then we were relying on the nature of the function to calculate what exponent it was being put up to, right? But now we can pass an exponent because we're going to have one function that will calculate all the possible powers for us. You could pass in 10, you could pass in 50. Doesn't matter, we want this function to be able to calculate it for us. Okay, so this is what we would call a special case. Okay, like I mentioned at the top one was the special case. In the event of the exponent being 0, as in the power of 0 function, right, we're just going to return 1. And this I'll get more into later when we really talk about recursion, but this is what we would call a base case. This is a special case that will allow you to say, hey, you don't have to do any more work because there's no need to calculate when you're raising it to 0. Okay? So now we need to be able to calculate the exponential value of a number without writing a function for every power along the way, right? And this is where it really starts to come together, okay? So let's look at our previous solution, right? Every time we go up from when we go up, I'm saying like go up the page, right? We're using the previous function, right? So we're just calculating something times the result of the previous function, okay? So for each power of n, we're returning the result of multiplying the base by a power of n minus 1, right? And you can apply this box right here, this yellow box, base n equals base times base of n minus 1. And n is just the exponent in this case, in case you're unfamiliar with n. So you can apply what's in this yellow box to all of these functions, right? It's the exact same thing. It's base each time times the answer from the previous one. Okay? Can I see B's or P's? Does everyone understand how this is working? Base times base n minus 1? All right, once again, guys, I'm going to throw out the, if you have P's, not that P's aren't always important if you have one, but put it out there now because this is an important principle in what we're doing, right? This is the main lesson of the day. All right, I see B's across the board. Excellent. All right, so here's our note, right? It says make a note summarizing this. Okay, so we know that we're going to multiply base by whatever base times exponent minus 1 is, but how can we determine what that value is, right? What we can do is we can use the exact same function, right? So just like before when we were calling power of 3, instead of calling a different function, okay, we're going to call that same function, okay, but instead of it just being a fixed function, as in the case of these previous functions, it's going to be our same function, okay, passing in the base because base is consistent, and we're going to pass an exponent minus 1, okay? So let's kind of verify our approach, okay? And if you guys have any questions about this, maybe hold up until after the example. That way I can kind of explain what's going on, right? So first we call just normal power of 2 to the 4, okay? That's going to return 2 times power of 2 to the 3, okay? And then power of 2 to the 3 is going to return 2 times power of 2 to the 2, okay? And then that's going to return 2 times power of 2 to the 1, okay? And that's going to return 2 times power of 2 to the 0. And we already know that anything raised to the 0 is 1, so that should just return 1. Okay, and there we have it, 2 times 2 times 2 times 2 times 1, which is 16, right? All right, so if you understood, it's times 1, not plus 1. So guys, if you understood what went on in what we just did, pat yourself on the back because that's recursion, or repetition as this is calling it. Okay? Let's see where this is headed. Hold on, I think we've only got a couple more slides. And right, since you're multiplying by 1, that's the same as just multiplying by, not multiplying by 1. And so now we can sum these up, right? We multiply 2 times 1, we get 2. We multiply 2 times 2, and we get 4. We multiply 4 times 2, and we get 8. We multiply 8 times 2, and we get 16. Okay? And that is our final result. Okay? And that's it for repetition with functions. So this is perhaps the most important B's and P's of them all. Oh, don't worry about it, man. Can I see B's or P's in the chat? Did everyone understand what was going on here? Any questions? Now's a great time for questions before you work on exercises. All right. I see 1P. Mr. Richard.
Yeah, that's from me. I need to figure out my internet because it was kind of jumping around while you were explaining this, which was unfortunate. Do you mind just doing like a quick summary?
No, not at all. So were you here, Mike, were you here for the right side? Do you understand what's going on over here? Mike? Oh, is that?
Oh, it's Dave. Sorry, that's Dave that's talking.
Oh, my bad. I thought I saw...
There's 2 Richards.
Oh, that's why. Okay, my bad. All right, sorry about that.
No
Dave, do you understand what's going on? Do you know what's going on the right over here?
Yeah, I understand it from each of the functions. So power of the base of 0, it's always going to return 1. That was that you actually put that statement in. If it's power to the 1, again, you're multiplying it by power 0. You're essentially just using the same function to at each layer. And yeah.
Exactly. So the key of what's happening, though, is that each of these can be summarized as saying, hey, take the previous result of like power to 3 and multiply it by adding on a new times base. Okay, so that's what you're doing every time. So if we work top to bottom, right, we start at power 1, and then when we go to power 2, we just take the result of that and we add on times base. Then when we go to power 3, we take the results of power 2 and add on times base. Right? So really, this is a problem that's being broken up into small chunks is really the key. That's what recursion is, okay? So what's going on here is we're taking what's on our yellow sticky over here, and we're applying it to this problem, okay? We're taking our first case because the first case of raising it to the 0th power has no thing that you can do below that. It's just, if it's 0, return 1, okay? But then in this new return statement, all we're doing is we're saying return base times base of n minus 1. And that's what this is, base of n minus 1, because it's saying call the same function, okay, call itself, it's calling itself, right, with passing in the same base value and then exponent minus 1. So if we pass in 4, the first time it does this return, it's going to call power of 2 and 3, okay? So then you can see that when that power goes, okay, when it invokes that power function, it's going to then call power with 2 and 3. So then is exponent equal to 0? No. So it's going to say, okay, cool, then return base times power of 2 to the 2. Okay? And really, it's going to keep iterating through until it hits exponent equal to 0, in which case it returns 1. Okay, but the key is that all of those power calls are going to be multiplied by the base before them.
Okay, so I think that's what I was trying to figure out, because I understand the logic. I was just trying to understand how it was actually looping through this multiple times.
Yeah, exactly. So like a great way to look at it is almost like imagine if you've got this power function that's a box. Okay, you're gonna like return something times another invocation, and that new invocation is gonna go inside that box. So you're still gonna have whatever you had before, like base times, and then you're gonna invoke power again, and then that's gonna have base times. So then you're gonna have base times power 2 to the 2, and then that's going to have a smaller box inside of it. So it's all contained, which is why you can then just multiply out all of the 2's.
Yeah.
Okay.
Okay. Thank you.
Yeah, excellent, Dave. No problem. All right, guys. I don't see any more E's. Any more P's. So any questions about this before we start working on the exercises?
Is there any way that you could do like an example? I mean, so I guess I'm kind of confused as to what's going to log here. Is like, I mean, 16 is just going to be all that consoles, right? Or
16 will be the only thing that consoles. Because like, the example I just tried to say is that all of this is happening just like by the interpreter. The interpreter saying, oh, cool, you want to call power again? Okay, let me do that. And it will call it, okay? And then it will keep calling power until it hits exponent of 0, and it'll say return. Okay, you want me to return then? Let me return all the way back to that initial call, okay, and give you that result, and which is why it will print out the result of 16. So yeah, I'm totally willing to do an example. Let's see. All right, so let's see. I wonder if this is too complicated for you guys. Give me a second. I've got a great idea to show you.
For anyone interested, this example is explained in Chapter 3 of Eloquent JavaScript.
Excellent. Yeah, definitely. If you guys haven't checked out Eloquent JavaScript, I mean, I hope this course is helpful, but you should check out Eloquent JavaScript because it is, in a word, eloquent.
Make sure you order Expedite on Amazon. I ordered it like 3 weeks ago, and it's not coming in like 2 weeks.
Order what?
I said order Expedited on Amazon because I ordered it like 2 weeks ago.
You know it's online for free, right?
Yeah, it's also
is it?
Yeah, it's online for free, and it has built-in like working code examples, so you can actually do the code and execute it while you're reading. Yeah, it's excellent. But that being said,
if you want a hardcover does exist, and it's a good book.
Yeah, one of the guys I graduated with from Hack Reactor, he had the paper copy, said he referenced it all the time. So, but yeah, if you just go to
where do you go?
Eloquent.js, just search it. Should pop up first thing.
Thanks.
Yep, eloquentjavascript.net. There you go. All right, cool. So I'm going to do an example for you guys. I'm going to use what's called a REPL, okay? REPLs are something that you guys can dive into if you want. I kind of told you what a REPL was at the beginning. It's called a read, evaluate, print, and loop, and that's what the Chrome console does, okay? Well, there's actually a nifty little site called REPLit, okay, REPL.it, and it will enable you to run code, write code on the left, and execute code on the right. So that's actually really handy. I should have told you guys about this sooner, okay? Rather than try to like hastily type stuff in the console and like make sure you hit Shift-Enter when you go a line down, right? Definitely try to use REPLit. It's really handy. So you hit Start Coding Now. Cool. We're making really good time today. I'm happy with how this is working out, definitely. All right. All right, so here's REPL, right? You can, like I said, write code on the left. When you hit the run button right here, it will print out whatever the result is, just like your console. Okay, so if I were to do function dog, takes in no parameters, and you console log or return 10, right? And then you invoke dog. Then you hit, what is the command? I should know this by now. Command enter. It will show you whatever the result is, okay? And it will show you that result independent of console logs. You don't need to have console logs, but console logs will still print out stuff specifically. So let me give you a scenario here, guys. Can I see JS Fiddle? I agree, JS Fiddle works well. I think as far as simplicity goes, though, you can't beat REPL. JS Fiddle is a little more complex. Can I see B's or P's in the chat? Do you guys know what the Fibonacci sequence is? Scrum scoring? I have no idea what that is. What is that? I was Scrum Master of several projects at HackReactor, and I've never heard of that. Oh, is that related to his comment, Scrum scoring, or?
Oh, just when we do sprints and stuff, a lot of times like the tickets get assigned points based on the Fibonacci sequence.
Oh, gotcha. Okay, cool. Oh, you're talking about at work. Okay, gotcha.
I didn't know if that was like a universal thing just through Scrum, or I don't know. But.
No, not at all. Okay, so, all right, guys. So there's something called the Fibonacci sequence, and it looks like this. It's a mathematical sequence that's found, like, oddly in nature quite a bit, I believe. Like, you can use its numbers to calculate, like, weird occurrences in nature, right? Isn't that kind of what it is? But anyways, the premise of it is that the previous two numbers calculate the next number in the sequence, okay? So you actually have 0 as the first number, right? 1 is the second number, okay? So by that logic, the third number is the sum of the previous two numbers. So the third number is 1, okay? The fourth number is 2. The fifth number is 3. And then 5, 8, 13, et cetera, okay? And then, wait, hold on, let me check. 8, 13, 21, I'll just keep going for making a point. 34, 55. All right, cool. Can I see B's or P's in the chat? Does everyone understand what the Fibonacci sequence is now? All right, excellent. I see only B's, so just keep in mind, right. So let's think about this, right? If we wanted to write a function that acts in the same way as what we just did, okay, we could write a Fibonacci recursive sequence that would calculate whatever the number was based on the previous numbers, okay? So let's try this out. I've done this, full disclosure, I've done this before, I just haven't done it in a while, so it's probably gonna be a little buggy when I first write it, but that's part of the joy of coding. So we're gonna write a function called Fibonacci, and it's gonna take an index value, okay? And an index value is just its position, right? So I think you guys have encountered index values a little bit in strings, maybe in the exercises. But if not, index values correspond starting at a 0th index to spots, okay? And in this case, we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's 11 items in this string because you count from 0, so it's 0 to 10, which is 11 things. Okay? So if that doesn't make complete sense, don't worry about it. Just know that we're counting from a 0th index. Okay? So we're going to write a function that will take a input of an index value of the Fibonacci sequence. Okay, so let me put that out beneath it just so you can kind of understand what's going on. We can say 0, 1, space 2, space 3, space 4, 5, 6, 7, 8, 9, 10. Okay, so just to show you, that's what its index value within the sequence is. Okay, can I see B's or P's in the chat, guys? Does that make sense what index values mean in this case? All right, cool. So we're going to write a function that will calculate the Fibonacci number at that index value in the sequence. Okay? So first we've got to check our preliminary cases, right? And what are our preliminary cases? Okay? Our logic is that each number is based on the sum of the two numbers before it. Right? So what does that tell us about the first two numbers of the sequence? Anybody? I'll free play. Call it out. Yeah, first two are fixed. There's no way to calculate them. We can't figure out what the first two numbers of the sequence are based on the previous two numbers of the sequence, because there are no previous numbers, right? So the first one that we can find that for is the third number, or in this case, the second index of the sequence, right? So that means we need a base case, right, or an if conditional, much like in the here, if exponent is equal to 0, right? That's the one that we couldn't calculate for. So we need the ones that we can't calculate for. Okay, so I'm going to start that off by saying this is going to take an index value, because we want to calculate the index value, the Fibonacci number at that index value is what this function is going to do. Okay, so we need to say that for if index is equal to 0, right, then we need to return 0. Okay? Actually, we could even say, I think we could actually just use this a combination one. Let's try it. Index is equal to 1, right? Then we could actually just say return whatever the index value is, because you'll notice that handily the index values of the first two match up to what the values actually are, 0, 0, 1, 1, right? So we could say just return index in that case. Okay? But you can't do that after that because it's relying on the addition of the previous two.
Why would you not use or?
You're right. I'm sorry. Totally my bad. Good catch. It should be or. That way you can check if it's this one or it's the other one, right? You can return the index value. Okay. Like I said, haven't done this in a while, so it might be a little buggy. All right, so that calculates our first two options, right? If it's 0 or 1, we know what to do. Okay, so now we have to do the recursive part, or the repetitive part. Okay, and in this case, we're going to throw in an else, okay, because whatever else is going to happen inside that else. Okay, and we're going to say return because we want to return initially. Okay, we know that whatever number we want to calculate is going to be the sum of the previous two numbers, okay? And we know that the sum of those numbers are going to be the sum of the two numbers before that. So I hope you can kind of see, as I'm saying this, that we can put in an expression that will, try to calculate it, and it'll see that it's a recursive call, so we'll say, okay, cool, let me go find out what that number is made from, and let me go find out what that number is made from, all the way until it gets to 0 or 1, and then it will just return the number. Okay, so in this case, we can say return Fibonacci, spell that right, Fibonacci of n minus, or index minus 2, okay, because you're taking the number 2 spaces back and 1 space back to make that number, okay, and then we're going to say add it to Fibonacci of index minus 1, okay, and that is, I believe, our solution, actually, unless I'm missing something. Because what this is going to do is that every time it executes, okay, if you entered in, let's run through an example, right? If we enter in, let's use something that we know, right? If we say Fibonacci, that's probably how you spell it, actually. I think it's 2 N's, whatever. Fibonacci of 10, okay, we're expecting it to be 55. So let's run it, and sure enough, we get 55, okay? Because what's happening is that when it looks at 10, okay, the 10th index value, it's saying, okay, cool, to calculate 10, we need to look at the value that's 2 back from 10, which is 8. And we need to look at the value that's 1 back from 10, which is 9. So it's going to go calculate those. And to calculate 8, it's going to look at 6 and 7. And to calculate 9, it's going to look at 7 and 8. And it's going to keep iterating back through this chain of index numbers until it hits 0 or 1. And then it will just return those because there's no more calculating to do. Okay, so if you want, I could say, I think this might get really messy if I try to console log this. Try to show you the iteration that's happening. Let's see, could I do, I think if I do this, it might get really messy, but I'll try it. Console log of index minus 2, right? And then console log of index minus 1. Okay, and then if we run this, yeah, it's going to spit out a huge amount of numbers, right? Because, oh, right, it's not, sorry, my bad, Fibonacci. I'm just going to print out one of them. That way it doesn't get too messy. Let me try that again. Let's see. So you can kind of see that it runs all the way back. Is that helpful? I don't know if that's not helpful. I'm not going to show that. So, I mean, I guess I could diagram this for you, but I mean, I only want to do that if you really have trouble doing this. And I think that going through the exercise will really help you understand what's going on. So does that help a little bit? Try to explain what's going on?
I have a question.
Please.
Why is the answer 55?
Because we're searching for an index value, right? And as I said, the index values start at 0 and go up and count up from there, okay? So this is what the Fibonacci numbers are on this first line. Yeah. And this is what the index values of those numbers are on the second line, okay? So we started at a 0th index, and that corresponds, right? All the way up until the 10th index value corresponds to the number 55, because 55 is the sum of 21 plus 34. Mm-hmm. Right? And so, right, so when we call Fibonacci of 10, it's going to say, okay, cool, give us the answer of Fibonacci of, so go calculate Fibonacci of 8 and Fibonacci of 9. And when it goes to calculate those two, it will say, okay, cool, well, what's the answer of Fibonacci of 6 and 7 and 7 and 8? And it will keep iterating back through the index values until it hits 0 or 1, okay? And then going back to the example here, right, it's going to just, wait, arrow keys. Right. Okay. It's going to say, okay, cool. Give us the previous result, okay, times whatever that number is, okay? Give us the next result times whatever that number is, and it will keep going until it hits our base case of 1 in this case. It'll return 1, and then we just multiply those all together. In the example that I'm working through, instead of multiplication, it's addition. Okay?
Okay.
Does that clarify things at all?
Yeah, I think I get it.
Okay. Can I see you guys general B's and P's in the chat if you feel like you have a good idea of what's going on and can tackle the exercises? All right. Seeing 1, 2, 3, 4. Oh, I always forget the Mac chat is way smoother, so I can scroll a lot easier. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, I see 13 out of 15. I'll take that, guys. If you have questions, feel free to stick around. Otherwise, feel free to hop off and start working with your pair. Make sure that your whiteboard link is updated, okay? For the purpose of these exercises, right, ideally try to, let's actually take a look at them as together really quick so we can see what's going on. We can say...
You broke up there. Can you repeat yourself, please?
Oh, yeah. I'm just going to go through and look at the exercises really quick so we can see what's going on together, just to make sure there's no surprises down the road. You know, in line with the whole message me if you are having trouble. Also message me if you find a problem that seems like, you know, ridiculously hard. Okay, and then I can help you. Either it's a, you know, you don't quite understand the problem, or it is ridiculously hard, and then I can tell everyone, hey, like maybe don't worry about this, and we'll go over it as a class. Because, I mean, that does kind of happen sometimes. I haven't seen it happen yet, but it's quite possible. All right, so here's today's repository, which I already linked you guys. We're going to be working in Intro to Repetition.
Are you going to want us to jump back in after the exercises today? Like as a group?
Yeah, maybe I'll try to run through another example at the end. It really depends on how you guys are doing on these exercises. That's the thing about end of the class lectures, is that it really depends on how things are going. If people are having lots of trouble and don't really seem to be getting it, I'll do another like try to reinforce concepts one. Actually, I think I have a couple things I wanted to tell you guys, just like important things other than housekeeping. So yeah, I think we'll get together for at least like 5 or 10 minutes, okay? So that should give you a solid hour 15 to work on it. Think about it over the weekend and tackle it again on Monday. All right, so this is a pretty simple function, factorial function. All right, so guys, keep in mind that all of these basic requirements functions, okay, and really like everything here, doesn't want you to use loops because we haven't learned loops yet, okay? So if you haven't And try to avoid using loops if you know what they are, okay? Try to do them all in the manner of how I just showed you by doing recursive calls, okay, to a smaller version of the problem, okay? That's the key with what we're doing. You're making a call to a smaller version. So with the powers, you're saying, give us base times the smaller version, give us base times smaller version, et cetera, et cetera. And all of these should be doable with that from what I saw. Oh, wow, I didn't realize that this was one of the exercises. You guys benefited from me not reading the exercise super close because that's the exact problem I just did. All right, so that should be easy for you, okay? And then more practice. Yeah, guys, I mean, just try to get as far as possible. You know, like I said, I'll definitely be giving you more time to work on Monday. I mean, you should ideally take a look at it over the weekend, try to like solidify your understanding, maybe do some reading about it. All right, but feel free to jump off, you know what you're doing, okay? Can I help you guys? Muted? No? You good, Chris? Cool.